Cool. Hi. Okay, yeah, so we're gonna play an imagination game, I guess. I'm Brandon. I'm a founding engineer and CEO of o1labs, and I'll tell you more about that at the end if we have time. So cool. Yeah. So what do you want? Let's say. Here's a version of like a cool platform. We want something that developers can build on easily. We want something that's powerful enough to actually like tap into the underlying proof system of our platform. We want anyone to be able to participate safely as an operator or as a user of the system. We want developers to be able to tap into that and build applications with privacy, but still interact with some global shared state, even in a system with untrusted actors. And we want to build on top of others through that shared state and scale. So, okay, great. So let's like break this down into something that's easier to digest. Cool. So if we want something to be easy for developers, I think like objectively that means composability, and I'll talk more about what I mean by that. Privacy is straightforward. Decentralization has a lot of vectors. There's like a bunch of components in your system, and you want to decentralize all of those. We want developers and users to act in the system in like a nice decentralized, trustless way. So I'll talk all about that. Computational efficiency. What I mean by that is we don't want to redo computation or pay extra for work that we want to do. And of course, like a lot of people should be able to do a lot of things at the same time. That's scale. So, okay. How do we do that? All right, so like, sharks are snarks. So there's going to be a lot of sharks. Okay, composability. We want easy composability while still getting like the juice of our system. I think about composability as like a mechanism where you can take simple building blocks that are really easy and make a lot of sense, and you can mix them together to make something like a little bit more interesting, and you can take that interesting thing and mix it together again with like a simple thing over and over and over again, and you get like crazy, awesome stuff. And if you think about that when you're like taking something that you build and you're mixing it again with itself, that's like some kind of recursive loop of sharks. And so like, so how does that translate to like our platform here? We need like proof recursion, and we want it to be first class in the sense that developers can actually, it's not just that our platform is built on top of some recursive proof system, but that developers can use that recursive proof system to compose things together. And it should be unlimited because we want to be able to do lots of stuff. Well, okay, so like how do we make that available to developers? Well, let's make recursive proofs recursive functions. Developers know how to use functions, so you can unlock the door of recursion. That's why I picked that image. Okay, and developers, like if you want to reach a lot of application developers, then you should use like JavaScript and TypeScript. Cool. Okay, so another vector of composability. If we have this like deep access to our proof system, then in addition to exposing like a thin layer on top, we could like stick a ZK VM on top. And then developers can be able to mix in like Rust and Go and C through the ZK VM. And through recursion, we can combine these things together in nice ways. We can cook our stuff. I don't know. Yeah. So okay, another vector. When you're like building some system, it's good to have people be able to like stand on the shoulders of each other, I guess. And one good mechanism for realizing this is through contract composition and tokens. And this is like contracts being able to call contracts. And we can do that in a system, on a ZK platform, like in a lot of ways. But I guess one way is, you could have different independent, changes to the state machine be kind of separated, and then when you make function calls You can represent that as like a tree, right? Like you can call a function, call a function, call a function, return, 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 call a function, right? And if you encode this into a circuit, the cool thing is you can reuse the same circuit for tokens. You can have like the top of the tree control and set like rules on top of how people are using the tokens, but you can still do this in a way that preserves privacy, which is cool. So, okay, that's composability. Like we want, through direct recursion, or through contract or token composition, and if we use JavaScript and TypeScript, it makes it easy, and mixing in ZK VMs makes it better. So, cool, privacy. Okay, like this, you'd think you get this for free with ZK, but like you only get it for free if you actually do the work client side. Because as soon as you're proving something away from you, then like you have to send your witness data to the to the prover. So we need to prove client side, or at least partially. But if we do this, this introduces new problems. One is performance, but that's like straightforward. But another thing that happens if you're working on a state layer that's shared and composable and people can build on top of each other, you have these race conditions that pop up where two users are concurrently accessing something at the same time, and so we have to like build in mechanisms for managing that. And one way you could do it is you can use like an action reducer system, like Redux or Elm architecture on the front end. So like basically two users concurrently can say like, let's increment some state, and then later another user or an application service can reduce that state and actually apply everything. And if you have some tolerance on how much of the actions you reduce, then you basically completely remove race conditions, which is nice. And it's still like not that hard for developers. Cool, so decentralization. We want, ideally, like the operators to be able to run the system on retail hardware. So that means either the work has to not be too expensive or we have to break that expensive work into pieces. If we have a system that's like sequencing transactions, then we want to decentralize the sequencer. And that means you have like some kind of blockchain-like system with a consensus mechanism with your favorite properties. We want to decentralize the prover. So that means, for example, like buffer proving work, farm it out to a marketplace. We want to decentralize user interaction. So with our applications, this is something that a lot of platforms aren't thinking about enough, I think. Like when a user is using like a DApp, either they're so sophisticated that they're running a node in their basement, in which case they actually are connecting in a nice, like decentralized way, or they're connecting through some like central relayer, and this is not ideal. But if we have like this amazing ZK platform, then we should be able to like use a ZK proof to kind of break this loop. So we can do that with like a proof of everything all at once, like a tiny proof that represents the whole system. So got to have a good shark picture for that. And if you have this small proof, then like this can be used in a browser directly, or like even on a phone. So like if we think about this, it means that like the whole blockchain needs to be in a snark. Like every consensus rule, every computation by every user has to like roll up into the snark, and it has to be consistently aggregated forever, incrementally, as people interact with it over time. And this introduces like cool stuff like we have to put all the consensus logic in a snark, and sometimes you have to use real numbers for some algorithms, but you can use like a Taylor series approximation for those things, and that you can represent in a circuit easily. So there's like lots of cool tricks, and then that's enough decentralization. So we decentralize our participation. We sequence things, which means we're doing some kind of consensus, and we can do that in a snark. We want to decentralize the proving, and that we can like buffer the work and farm it out to a marketplace, and then decentralize end users' usage of the system, which entails putting everything into a tiny proof. Okay, computational efficiency. Yeah, so how do we think about this? Well, if we have client-side compute, then it's cool because like gas becomes predictable. And you know, sometimes we can even like remove backend services entirely. So like people who are spending money on some service, like you can just make your users do the work. So you kind of get that for free. And scaling, I think you know, you kind of get this for free as well. If you have this like tiny proof of everything and you have recursion, well, we can make ZK rollups super easy for people to build on the platform and developers to make themselves like even in their applications. Yeah, what do we talk about? Easy composability through recursion and client side using JavaScript. We have contract calls and tokens that we can handle with clever circuit reuse. We need client-side compute with privacy. For decentralization, we want to decentralize like people participating through building with like retail hardware in mind, sequencing by like using consensus, like putting consensus rules in a snark, proving by buffering work and then farming out to a prover marketplace, and then you know rolling up everything always incrementally into a proof of everything, and then we can get like actual decentralized end user usage. We get computational efficiency with this system kind of for free, and we get scaling through the tiny proof and then recursion. Cool. So, I mean, I don't know if this was a surprise, but I guess you could tell I was shilling. I don't know. This is Mina, and we have like designs and implementations for like all of that. Some of it is in progress, but a lot of it is already done. So just to like go over that, you know, on Mina's mainnet, which has been out for the last 3 years, we have this tiny proof of everything, but just for payments, using a pickled proof system. That's what we call it. And we have like sequencing decentralized. We have the Ouroboros consensus mechanism inside of Snark, and we do like the cool Taylor series thing and other like fun tricks. We have a decentralized proving marketplace built into Mina, which is called the Snarketplace, which has been powering it for 3 years. And what's coming soon, like really soon, and I'll quantify that, is a few other things. So one is this client-side compute with what we call ZK apps. You know, we have this like cool ZK VM system that's like very low level in the sense that it's very close to the proof system, so it's really efficient, so that we can do off-chain computation like on the client's machine. It's composable through these like call forests that I showed before, and you know we use action reducer style reconciliation and do other fun stuff. We have like a more powerful proof system coming, which you know is called pickled kimchi with some pickles recursion on top, and it's just better, faster, more powerful, and all the fun stuff. We have coming probably like a few months after this upcoming mainnet upgrade, like realizing the vision of having like full nodes in the browser or the phone through OpenMina, and then like users directly connecting to the network through that when they're using applications. We have a programmable TypeScript framework called o1.js, where recursive functions are recursive proofs. And we have like more than 2 years of iterations of like playing, you know, having devs use this and stuff. So if you haven't checked it out, I really recommend it. It used to be called Snarky.js, but we renamed it. So it's o1.js now. And yeah, we expose like the stuff in the proof system. So like you can use custom gates directly. And you know, we have a bunch of libraries like ECDSA and nullifiers, and we have nice abstractions and encourage people to build more. We have bridges coming soon to the EVM. There's a bunch of different folks working on this, on different versions of this. We have, I'm just gonna go really fast. We can scale with rollups and rollup SDKs, and there's a couple of those that are gonna launch soon. And you know, just to quantify this, because people say soon all the time and everything, like all the testnet phases are done. but the upgrade tooling is done. Private tests on upgrades are done. And on Tuesday of this week, we hard forked our DevNet successfully, and that's like the network that most closely matches our mainnet. So, really like mainnet is next. It's just, like, are all the exchanges and stuff ready, and then we can hit the button. And then, but this is just the first step, like, so it enables all this cool stuff. There's more that we want to do. So as I mentioned, like, we've been working on a high-performance MIPS ZK VM, which we've been using for an integration to help like Optimism introduce fraud proofs. We're going to integrate that into Mina. We have a lot more work on performance to do, and powerful capabilities and bridges and L2s and all this cool stuff. So before I run out of time, so yeah, o1labs is where I am the CEO, I guess, these days. We incubated Mina. We still work on it. We do a lot of ZK stuff. And a bunch of other cool things like in and around Mina. We have 1 million open roles. I don't have time to walk through them all, but they have cool names. And even if you don't fit in a role, just apply anyway, because we can make a role. So that's it. And I just ran out of time perfectly, right?
Thank you, Brandon. I think we can take one question from the audience.
Drats. Too fast.
Please.
Hi, Brandon. Thanks for the great talk. You mentioned a lot about client-side proving. I wanted to ask you, like, in general, if you think about client-side proving from a mobile phone, right? You're working in a memory-bound and energy-efficient system. You need a memory-bound and energy-efficient protocol to actually make it feasible, right? So do you think with the way you're building with Plonky, you think you'll be able to get to that situation?
Yeah, I'd say, I'm not going to lie, right now on a phone, especially in a browser on a phone, like, it's going to be slow. And yeah, more complex contracts, you end up hitting memory errors, like running out of memory. So we have more work to do there. I think it's all engineering, though. Actually, there's not much. At least we believe like our proof systems are like close. We have a couple ideas to do other stuff, and then it's just like, okay, like be clever about reusing buffers and then taking advantage of like GPUs on the devices, things like that.
Thank you. Thank you, Brandon.